Hello friends, I am Satyendra and today in this video I am going to explain you what is the normal Zeeman effect. Okay, so we will discuss only the normal Zeeman effect in this video. Before proceeding, I want to tell you something that in this video there are some advertisements that are coming at the top of this video. So I am not at all responsible for those advertisements because this advert because this is this app this because I have not purchased this app and the advertisement is coming because of that. Okay, so don't follow that. Let's only please look at the lecture videos which I am explaining to you. Okay, so today we will discuss the Zeeman normal Zeeman effect. So let's see. So the phenomena of splitting the spectral lines emitted by atoms placed in a magnetic field is called the Zeeman effect after its discoverer P. Zeeman. Okay, so what actually happens that when you if there is an atom that emits some light, okay, and if you place that atom in the magnetic field, then there will be some additional lines that will come from that atoms. Okay, that is called the Zeeman effect. Okay, and it is called Zeeman effect because of its discoverer P. Zeeman in 1896. Okay, okay, now in some cases the spectral lines split into three lines and is known as the normal Zeeman effect that can be explained on the basis of classical physics. Okay, now in more general cases the splitting are complex and most lines show more components, 4, 6 or even more, that cannot be explained classically and and is termed the anomalous Zeeman effect. Okay, which can only be understood on the basis of quantum ideas and spin. Okay, so now you understand that what is the point. Okay, okay, let me explain you. So in normal Zeeman effect, okay, the spectral lines split into three. Okay, usually split into three, and that can be explained on the basis of classical physics. Okay, now if we talk about some more cases, then in general, okay, the splittings are complex and most lines shows more components like 4, 6 or even more, that that splitting cannot be explained classically and is termed as anomalous Zeeman effect, which can only be understood on the basis of quantum ideas and the spin concepts of spin. Okay, okay, so in this video I am going to explain you the theory, and that will be only for the normal Zeeman effect. Okay, okay, now let's look at the experimental setup and observation. Okay, so this is the experimental setup. Okay, let's look it more closely. So in this experimental setup, this is the electromagnet, this is also the electromagnet. Okay, we so okay, and this is called electromagnet because these magnets are formed due to direct current. Okay, okay, you can see that there is a supply of current. Okay, and there is a solenoid like structure. Okay, so now due to this two electromagnetics magnets, this will form one pole that is called P. Okay, and this will form another pole that is called BP. Okay, so this is called BP because of a board pole. Okay, board pole means in this electromagnet there is a hole, that you can see that there is a hole, there is a bore. Okay, so that is why this pole is called bored pole or BP. Okay. Okay. Now, now you can see that between these two poles, okay, between these two poles P and BP, there is an atom S is placed, and this can be thought as a source of light. Okay, and this atoms emits the light in two directions. First is this direction. Okay, that is called a longitudinal view. Okay, that is called longitudinal view, and the other is this line, this direction, and this is called the transverse view. Okay, and this instrument is the, 1 minute, and this instrument is the spectrograph. SP stands for the spectrograph. Okay, and here also the light that comes is sensed with the help of spectrograph. Okay, SP, that means spectrograph. Okay, now, so now you have seen the experimental setup. Okay, so you have seen everything now, and now let's proceed further. Okay, so let's proceed. So what is the observation that we get? Okay, so let's see the observation. So we have to first look at the observation. So when the source of light S is placed in the magnetic field, okay, the spectral line undergo following striking modifications. Okay, okay, so let's come to our diagram. So you can see that here is the source of light, that is atom, and because of these two electromagnets there is an electromagnetic field B in this direction. Okay, so this is the important point that you have to know. Okay, now let's see the observations. So there are basically two observations. So let's read the first observation. So when the spectral lines of frequency nu, okay, okay, 1 minute just. So when the spectral line of frequency nu is examined parallel to the field, that is the longitudinal view, each spline appears to split into two and are circular polarized. Okay, so let's see. Okay, let you understand what this means. So as the earlier experimental setup that you have seen, that the magnetic field B is was in this direction. Okay, and there was the source of light S. Okay, now, now the first observation was this longitudinal view observation. So if you look in this direction, okay, then you will get two spectral lines. First line is here and the second line is here. Both of these lines are circularly polarized. Circular polarized. Okay, circular polarized. Just give me 1 minute. Okay. Okay friends, so okay, you have understood this thing. Okay, okay, now this was our first observation. Okay, let's again read the first observation. Now you have understood. So when the spectral line of frequency nu is examined parallel to the field, okay, longitudinal view, each line appears to split into two and are circularly polarized. This was our first observation. Okay, now you can also see the frequency of these lines. Okay, so the frequency of this line is the first frequency is this, and the second frequency is this. Okay, okay, Now let's come to our second observation. So in the second observation, we look the source of light through the transverse view, okay, in this direction, okay. So in this direction, when the source of light is viewed, then we get three lines, okay, first, second and third, okay. There are three lines, okay. Okay, now this line is this particular line has the same frequency as the frequency of this atom originally, and means the light that was originally emitted from this atom, okay. So this is the same frequency of that, and this line is parallel polarized. This line is plane polarized, and it is the polarization is parallel to the to the direction of the incident magnetic field, okay. So and now we have to look at this, okay. So this line is also plane polarized, and its direction of polarization is perpendicular to the magnetic field B, okay. And this is also the the plane polarized light, and this is, and its direction of polarization is also perpendicular to the direction of the magnetic field, okay. So there are three lines. So this is our second observation. So let's read the second observation. So now we have came to our next means we have came to our second observation. So let's read. When observed perpendicular to the field, that is transverse view, each spectral line is split into three lines or triplet, the central line appearing in the same position, okay. The central line appear in the same position as the original line of frequency nu. It is plane polarized with vibration parallel to the magnetic field and is called the pi component. And this is important for you to remember this pi component, this symbol pi, okay. So this is what I have already explained you, okay. So let's come to our further observations, that the two other components called the sigma components, okay, are symmetrical about the central line, and plane polarized with vibrations perpendicular to the field. So this thing actually I have already explained you in the diagram. So let's go to the diagram, okay, again. So one. So yeah, we have came to our diagram, okay. So that I now let's see, okay. I have already explained you that this was the same as the original, and and you can see that this was the another line and this was the other line, okay. And in this this I have already explained you that this was polarized perpendicular to the field, and this was polarized parallel to the field, and this is polarized perpendicular to the field, okay. now now you can see that this line is called, which is polarized parallel to the field, this is called the pi line, okay. And the line which is polarized perpendicular to the field is called the sigma line, okay. And this is also the sigma line, okay. So this concept is clear to you, okay. Okay, now now let's see the mathematical explanation of the normal Zeeman effect, okay. So in order to understand the normal Zeeman effect, we have to take some quantities. Okay, now, so you have to consider an atom that we have seen that the source of light, as that consider that there was an atom. Okay, so let an atom and have the orbital angular momentum L. Okay, only. So in the normal Zeeman effect, to explain the normal Zeeman effect, only the orbital angular momentum is taken into the consideration, and this is an important point that you can note down. Okay, okay, and that atom is placed in an external magnetic field beam. Okay, along these z axis, along this z axis. Okay, and q and 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 the atom is in the quantum state of the energy E. Okay, so the atom is in the state, which state, and that state has the energy E. Okay, and the orbital angular momentum quantum number is L. Okay, 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 let me explain you more clearly. Okay, so to form the mathematical theory of this, you have to consider an atom that emits the light, and that atom has the orbital angular momentum L. Okay, and that atom is placed in the external magnetic field B. Okay, and that the direction of the magnetic field is in the z axis, and the atom is in the quantum state. Okay, and the atom is in the quantum state with energy E, and the orbital angular momentum quantum number of that state is L. Okay, so this you have to note down to formulate the mathematical theory. Okay, so now we all know that, you all know that if an atom, so just 1 minute. So you all know that if a magnet, okay, if a magnet is placed in a in external magnetic field, then there is some interaction between that magnet and the external magnetic field. Okay, and due to that interaction, there that due to that interaction there comes some potential energy. Okay, so that potential energy is, let me explain you what is that. Okay, so we that is that we all know. Let me write here. Okay, if a external bar magnet, for example, like this is some bar magnet, that is the south pole and that is the north pole. Okay, and that magnet is placed in some magnetic field like B here. Okay, so if a magnet is placed in that magnetic field and there is an angle theta, okay, between this between the magnet and magnetic field. Okay, then the potential energy of this bar magnet U is just minus magnetic moment. Okay, magnetic moment mu dot B. So that is the dot product. Okay, so this is the potential energy, and this potential energy is called, also known as the interaction energy. Okay, okay, so here also the same thing happens actually. Okay, so we know that our atom has the orbital it has some orbital magnetic moment, because the electrons revolve around the nucleus, and due to that the orbital because due to that orbital magnetic moment generates. Okay, so that is the orbit there. This is how the orbital magnetic moment come into the consideration. Okay, and due to this orbital magnetic moment, the atom will act like an electric dipole, sorry, a magnet. It will behave like a magnetic dipole. Okay, so that will behave like a magnet, and that magnet is placed in some external magnetic field B. Okay, so due to that small magnet, atomic magnet, and external magnetic field, there will be some interaction. Okay, so because of that, so the interaction energy delta E of the atom due to interaction between orbital magnetic moment mu L of atom and external magnetic field B is, okay, so that interaction, or the potential energy of interaction is this much. Okay, and if you are unaware of this thing, then don't worry, you just have to remember this. Okay, okay, for your exams you can remember this. Okay, so this is how the interaction energy between the atomic magnet and the external magnetic field is written. Okay, and you can also remember the unit of this magnetic field, which is ampere per meter here. Okay, and it is not at all Tesla here. Okay, okay, it is the ampere per meter. now now this is the interaction between the atom and the external magnetic field, and this is the dot product. Okay, and this dot product is written is in this form. Okay, okay, in the form of cos theta, in this form. Okay, we all know that this is the vector, this came from the vector algebra. Okay, okay. Now here this you can see that there is a theta, and this theta is the angle between the magnetic field B and the magnetic dipole. Okay, this is the direction of magnetic dipole, so theta is the angle between B and mu. Okay, okay. now now you have to know that the you have to understand, or you have to know that the magnetic moment is given by this formula, and if you are unaware of this thing, then don't worry, you don't have to worry at all, you can just remember this thing. Okay, you can just remember this for your exams. Okay, now the angle between the cosine of the angle between the B and the magnetic dipole moment is given by this formula, and this also you don't have to remember too much. Sorry, you don't have to understand too much, you can just keep in mind this thing if you are unaware of this thing. Okay, so I am not going to take you in that much detail how this thing came, because then we will divert from our current topic. Okay, okay. Now if you remember this, then you can also know that this Lz has this value, and that has came from the quantum mechanics, and this is just L, and you really truly speaking, for the current understanding of the normal Zeeman effect, you can just keep this as a fact and you can remember this thing. Okay, okay. Now what I am going to do is that I am going to put this value and this value back in this equation. Okay, so I have substituted the values here. Okay, and you can see that something cancels out, like this L and L got cancelled, and I am only left with this quantity. Okay, and this quantity is further equals to this Bohr magneton. Okay, and then finally my delta E is equals to this much quantity. Okay, so my interaction, so the interaction delta E finally is equals to this much. Okay, and this is our main per interest. Okay, so let's see further. So so we know that as I have already told you that the atom was in the state E. Okay, the atom was in the state E. Okay, and the energy, that state E, okay, is equals to, that state E is equals to E naught plus the interaction energy. Okay, so let me explain you this thing, what is this, is what this stuff is. Okay, okay. So the energy of the state, energy of state E. Okay, E is, see, so energy of the state E. So so this was the energy of the, this was the energy of state of atom in absence of magnetic field. So I forgot to write here in absence. Okay, so this was the energy in the absence. This was the energy of the state of atom in the absence of magnetic field, and in the presence of magnetic field, the atom interacts with the magnetic field and it forms the further interaction energy, which is this much. So finally, in the presence of a magnetic field, the energy of the state, that is E, is the sum of this energy and this energy. Okay, so so you can read that here, that E is the energy of the atom in the presence of magnetic field, and this was in the absence of magnetic field, and this was the just the interaction energy. Okay, okay. Now, you can important point here is to see that, so important point here is this is that here this energy E, okay, is the sum of this energy and it is the sum of this energy. Okay, okay. And here you can see that there is a term ml. Okay, and this ml is very important for you to now understand the normal Zeeman effect. Okay, so the ml have the values 2l plus 1. Okay, and it ranges from minus l to 0 up to plus l. So in total it has the 2l plus 1 values. Okay, so that means since this ml is associated with the energy, so you can so see that, so the energy will also have 2l plus 1 values. Okay, energy will also have 2l plus 1 values, and each slightly different and determined by ml. Okay, so the atom can make transition between these 2l energy states, and these transitions are controlled by the selection rules. So here comes the important thing, that is the selection rules. Okay, okay. So now, so you, as I have explained you, that here there is a quantity associated quantity ml have 2l plus 1 values. Okay, so that means that this energy E will also have 2l plus 1 values. Okay, so there are 2l plus 1 energy states of the atom. So atom can easily make the transition between 2l plus 1 energy states, and when the atom makes the transition between these energy levels, it emits the light of certain frequency, and those lights appear that is why you see that your single line will split into other lines. Okay, so okay, so let me explain you in more detail. Okay, so just hold on, don't worry, you will understand everything in this video. Okay, so now you have understood this thing. Okay, okay. So you have understood that there are 2l energy states, and these, the atom can make transitions between these energy states. Okay, okay. So these transitions are controlled by some rules, and those rules are called the selection rules. Okay, okay. So selection rules are here. So in order to make the transition, the change in angular momentum quantum number should be plus minus 1, and the change in this quantity, that is the delta ml. Okay, so the change in this thing should be 0 or plus minus 1. okay, only for these values of ml and delta L the transitions are possible. Okay, so you have to know and remember these things. Okay, okay. Now, in order to explain you how the transitions actually come and how the splitting actually happens in normal Zeeman effect, you have to now let us take some examples. Okay, so let us assume let us assume that the system, that is the system is our atom. Okay, that atom makes the transition between initial and the final energy levels. Okay, so we have two energy levels, that is first is the EI, initial energy level, and other is the EF, that is the final energy level, and the atom makes the transition between these two energy levels. Okay, okay. So as per our equation that I have already explained you. Okay, so let's see that equation. Okay, so this was that equation. Using this equations I can define IE and IF. Okay, so let's see, I have already done that. Okay, so here you can see that I have written the initial energy, okay, in this fashion, and I have written the final energy EF in this fashion using that equation that I have shown you. Okay, okay. Now what I am going to do is that now this is the initial state of the atom and this is the final state of the atom in the presence of magnetic field. Okay, okay. Now I am going to subtract these two equations. Okay, okay, so I have subtracted these two equations, and I can see, you can see that this has came and this has came and then this has came. Okay, so you can see that these things. Okay, so you simply have to subtract, and now this difference in energy is written as h nu. Okay, and this difference in energy is written as h nu 0. Okay, so this has came from again from the quantum mechanics. So if you don't know, you just have to, you just keep in mind this thing. Okay, okay. Okay, and then here also that this difference of ml is written like delta ml. Okay, okay. Okay. Now, so further my this equation, this whole equation, my I have divided this whole equation by h, that is the Planck's constant. Okay, and that Planck's constant, when I divide by that Planck's constant, I further arrive at this equation. Okay, okay. So now at this point I will explain you how this h nu has came. Okay, okay, how this came. So according to the quantum mechanics, when an atom makes the transition from final energy state to this, sorry, from the, so according to the quantum mechanics, when an atom makes the transition from this initial energy state EI, okay, EI, to the final energy state EF, okay, then the difference of energy is emitted in the form of light. Okay, and that light carries the energy h nu. Okay, so this is how the difference of energy is written in the form of h nu. Okay, so this is the quanta of energy. Okay, and that's the Planck's law actually. Okay, and from where the quantum mechanics actually originated. Okay, so for the timing you can just keep this thing in your mind. Okay, now you have finally, you have got this thing. Okay, okay. Now that in that equation I have substituted the values. Okay, so let's go to that. So in this equation I will further substitute the value of this Bohr magneton, and the value of, I will substitute the value of Bohr magneton. Okay, so let's substitute this value. So I have substituted this value. Okay, you can see that I have substituted the value. Okay, so at this point I can also substitute the value of h naught, that is h upon 2 pi, and I can further solve that, and that will give me this final equation. Okay, okay. Now I will show you now now I will show you the splitting of energy levels in magnetic field B for L equals to 0 and L equals to 1 state of an atom with angular momentum, with orbital angular momentum only. Okay, okay. So you can see the diagram here. Okay, so first is the S state. Okay, so we all know that L equals to 0 is S and L equals to 1 is P. Okay, and now there cannot be any type of transition from here to here. That is not possible at all, because for the transition delta L, okay, 1 minute, because for the transition this delta L should be equals to plus minus 1. Okay, this came from the selection rule, and here that condition is not satisfied, so that's why there cannot be any transition from here to here. Okay, okay. Now now you can see that here at this point the magnetic field was 0. Okay, now in the presence of magnetic field, okay, in the presence of magnetic field where the magnetic field is not 0. Okay, okay, so at that point, if the magnetic field is not 0, then you have already seen that there was an interaction energy. Okay, okay. So here at this point the energy will have only one value. Okay, that energy is, so the interaction energy, so you have already seen that interaction energy E was equals to, okay, so that energy was equals to mu b p ml. Okay, so that was your interaction energy. Okay, so at this point, okay, so if you only think at this point, okay, at this point, okay, so let me write the whole equation. 1 minute. Okay, so the energy of the state E, okay, okay, now that this is good. Okay, so you can see that in the absence of magnetic field, okay, in the absence of magnetic field, this was the energy level. Okay, and in the absence of magnetic field, this whole term is actually equals to 0, so there won't be any splitting at this point. Okay, okay, there won't be any splitting at this point. Okay, because the magnetic field is 0, and because the magnetic field is 0, and so this will be 0, and energy will only be equals to E0 at this point. Okay, but in the presence of magnetic field at this point, the magnetic field is present and B is not equals to 0 at this point. Okay, so since B is not equals to 0, so for L equals to 1 minute, so for L equals to 1, ml will have -1, 0 and +1. It will have three values. Okay, okay, so because of three values of ml, okay, 1 minute, because of three values of ml, okay, the E will have three values, so energy will level will have three energy levels, so there will be three energy levels. Okay, okay, So that is why there are three energy levels. For each value of m there are each energy level, so there are three values of m, so there are three energy levels in total. Okay. Now for s, okay, similarly there is for s. Okay, so as in the absence of magnetic field, s will not split. Okay, and in the presence of magnetic field also, the s will not split. So in the presence of magnetic field also, the s will have l equals to 0. So ml will have only one value, that is 0. That is why there is no splitting in s. Okay. Now now atoms can make the transition between these levels. Now atom can make transition between this bit from this level to this level. Okay, and let's see it how it makes the transition between these two levels. Okay, so it is followed by the selection rule. That is, we all know that delta ml by selection rule should be equal to 0 or plus minus 1. If this condition is satisfied, then atom can make the transition between from this level to this level. Okay, so you can see that here for this transition delta ml equals to minus 1, that is correct. So that transition can happen. For this delta ml equals to 0, so this transition is also possible, and for this delta ml is plus 1, so this is also possible. So there are three possible transitions that can then that an atom can make, and because of this transition the single line will come to split. So that is why you will see the three lights of different frequencies. Okay, so this will give you some frequency, this will give you some other frequency, and this line will again give you some other type of frequency. Okay, so we will use our this basic equation to find the frequency of the lines. Okay, so let's see. So you can see that at for ml equals to 0. Okay, so that means so that I mean that, so for this particular line the frequency is this much. Okay, because there is delta ml equals to 0, and for delta ml equals to minus 1. Okay, so for this line, okay, so for this line you get this frequency. Okay, so this is your frequency for delta ml equals, so delta ml equals to minus 1, and sorry, there should be delta. Okay, and this is your frequency for delta ml equals to plus 1. Okay, delta ml equals to plus 1. So there are three lines, 1 2 and 3. So you got three different frequencies, 1 2 3. Okay, so this explains the splitting of the spectral lines in the presence of magnetic field. Okay, so splitting means instead of one line or no line, okay, instead of one line or no line you see three lines, because now atom can make the transitions between those lines and can emit light of one minute, and can emit the light of three different frequencies. So this now completely explains you about the normal Zeeman effect. Okay, thank you, thanks for watching this video. Thank you.